10-3 Day 1, area of regular polygons. Before we begin with area of regular polygons, let's take a minute and write down all of the area formulas for the shapes that you see named here, and do this without looking at anything initially. So hopefully we have the following as our formulas for these shapes. Then also keep in mind, we've talked about area and circumference of circles. The area formula is pi r squared for a circle, and circumference could either be pi times diameter or 2 pi r. So now moving on to regular polygons, we have to remember, what is a regular polygon? It's a polygon that has all sides and angles congruent. And now in order to be able to find the area of a regular polygon, we first have to understand the parts of a regular polygon. So first of all, any regular polygon can be inscribed in a circle. So now because it's inscribed in a circle, you can say that a regular polygon has a radius, which is always the distance from the center. So the center is the exact same center point as the circle that the polygon is inscribed within. And the vertex, which is one of the corners of that polygon. So here we have a radius. And then we have a part of a polygon called the apothem, which is always going to be represented by the lowercase letter a. This is a perpendicular distance from that center point to a side of your polygon. So again, still not even getting to the area formula for a regular polygon yet. It's going to be at some point very important for us to be able to find different angle measures within regular polygons. So right now we're going to look at finding a few of those. The first one that we're going to find in this regular hexagon is angle 1. Now, first thing we have to know about angle 1 is that it's called a central angle, because the vertex of that angle is at the center of the polygon, and the two sides of that angle are each a radius of that polygon. So when we find a measure of a central angle, we're going to take 360 and divide it by n, and we use n to represent the number of sides of that polygon. Now, it also, n corresponds with the number of triangles that would be created if we drew all of the radii from each vertex to the center point. So n is not just the number of sides, it's the number of triangles, isosceles triangles for that matter, that would be created by drawing all of the radii in, which also tells us how many of these central angles there are. And since we have a regular polygon, all of those central angles would be congruent. So in this case, since we have a regular hexagon, we're going to take 360 and divide it by 6 to find out the measure of our central angle. The measure of angle 1 is 60 degrees. Now, the measure of angle 2, because I just mentioned that these triangles that are created here by drawing in these radii are isosceles triangles. Measure of angle 2 is exactly half the measure of angle 1, because we've learned earlier this year that in an isosceles triangle, the altitude from the vertex is the angle bisector of that vertex angle. So we can just take half of 60 and find that the measure of angle 2 is 30 degrees. Now, finding the measure of angle 3, there's a couple of different ways we could do that. First way is to think of the measure of angle 3 within just one of these small right triangles. If I've already taken out this 90-degree angle, that means angle 2 and 3 have to add up to 90. So 90 minus measure of angle 2, which we already know, would give us a measure of angle 3 as 60 degrees. The other way we could think about this is to go back to the isosceles triangle idea. We know we would have these two base angles congruent in the isosceles triangle. So we could take 180, subtract our central angle, which is the vertex angle, of 60, and then divide that by 2 because it has to be split evenly between those two congruent base angles. Again, you'd find the measure of angle 3 to be 60 degrees. Now we get to actually finding the area of a regular polygon. So before we actually get to the formula again, let's look at our shape. Our shape, keep in mind, if I draw all the radii in, is divided up into isosceles triangles. All of these isosceles triangles are congruent because of the fact that this is a regular polygon. So all we really need to focus on is just one isosceles triangle. And within that isosceles triangle, the height of that, the altitude, that is the apothem. And then the base of that triangle is the side length. So what a lot of textbooks use as the formula for the area of a regular polygon is to take half the product, meaning multiply, of the apothem and the perimeter. So the formula generally given looks like 1/2 A times P. I prefer that we use something different. So let's ignore this one. Let's use one that actually breaks everything down to the individual pieces that we need so that we just have a little bit easier time plugging everything in together to find that area. The formula I like us to use is 1/2 ANS. The A, the lowercase a, stands for the apothem. The N, again, stands for the number of sides of the polygon. And the S stands for the side length. Now, the reason we can use this instead of the one that we looked at first is because in a regular polygon, the number of sides times the side length gives you the perimeter. So that is going to be important if you're ever given the perimeter and have to work backwards. But I've found that this formula tends to lead people into being a little bit more successful when they're finding their areas because it shows them specifically all the small individual pieces that they need. So our very first example, we have to find the area of a regular decagon with 12.3-inch apothem and 8-inch sides. So in this section, it is going to be very important for you to recall some of those special names that we had covered earlier in the year for different types of polygons. So I know if I have a shape here, I can draw in 2 radii and an apothem, and I can label my side length being 8 inches and the apothem being 12.3 inches. Then we always start with our formula. So in this case, area equals 1/2 ANS. I can take everything and plug it in. I know everything at this point. 1/2 times the apothem is 12.3. There are 10 sides in a decagon, and the side length is 8. When I multiply all this together, I would find that my area is 492 square inches. Second example, we now have a regular octagon. The side length is 18 feet and the radius is 23.5 feet. So again, if I draw into my picture all the information that I know, I have my side length and my radius labeled. I have my apothem drawn in with the letter A, signifying that I need to figure out what that value is. So now we have to think to ourselves, how do I figure out what this apothem is if I'm given the other 2 lengths? Well, notice here I have 9 feet and 9 feet written in because, again, we know that this is an isosceles triangle with the 2 radii. So that means that not only is this apothem bisecting that vertex angle, but it's also the perpendicular bisector of the base, which happens to be the side of the polygon. So I have a right triangle where I know 2 of the 3 sides and I'm looking for the 3rd side. That is a classic time to use the Pythagorean theorem. The radius is the hypotenuse of that right triangle. Your apothem and half of your side length is are the two legs of that right triangle. So Pythagorean theorem would lead me to say that the apothem is the square root of 471.25. You'll notice that I left the apothem as the square root of 471.25 instead of typing it in the calculator and rounding off that decimal. This, again, is somewhere we don't want to round until the very end of the problem. So we're going to keep our apothem right like that. Well, now we have our formula, 1/2 ANS. Plugging in the square root of 471.25 is the apothem. Octagons have 8 sides, and the side length was given as 18 feet. That all being multiplied together. Again, always paying attention to directions here. We are supposed to round to the nearest thousandth. Very critical that we follow the directions and give the type of answer that is asked for or that is required. So in this case, 1,562.997 square feet would be the answer that we were looking for. So in that last problem, I just mentioned how important it is to make sure you're paying attention to the type of answer you're supposed to give, because now in the in example number 8, you'll see we're supposed to leave our answer in simplest radical form. So simplest radical form is a huge clue that we're either going to be needing to use Pythagorean theorem in simplifying radicals, or we may be needing to use some special right triangle properties. One thing that you cannot use when you're supposed to leave your answer in simplest radical form is any trigonometries. Sine, cosine, and tangent do not give us simplest radical form. So if I have an equilateral triangle and the apothem is 8 centimeters, I draw that information into my picture. Thinking about what my formula is to find the area of an equilateral triangle, because that is a regular polygon, I'm going to use 1/2 ANS. So you can notice here in the picture, all I have is one length. I just have the apothem. So when I just have one length, this is a time where you need to find an angle. The angle that we are needing to find is one of these top two angles, or remember, it's always half of that central angle. So to find the central angle, we did this just before on the front side of our notes. We're going to take 360 and divide it by the number of sides. So we have 120. So now we know this entire angle is 120. We only want half of that because we want to work with a right triangle here. So now we know that we have a 60-degree angle. So we can write that into our picture. This would be a 60-degree angle. Again, thinking back to the question, it says leave your answer in simplest radical form. This is now able to be called a 30, 60, 90 triangle. Since this is a 30, 60, 90, I would recommend that you label your short leg, the long leg, and the hypotenuse. Keep in mind, one of the pieces that you need for your formula is the side length, so you can label the whole thing as S if you'd like. So now just using 30, 60, 90 triangle properties, we could say that since the short leg is 8, we can find the long leg to be 8 times the square root of 3, and the hypotenuse could even be said to be 16, even though that hypotenuse isn't something that we need to plug into our formula. Now again, keep in mind that this apothem is the perpendicular bisector of the base as well as the angle bisector for that vertex angle. So we would have 8 square root of 3 as well for the other long leg in the other right triangle. So if we were to combine those two things, we can say that our side length is 16 square root of 3. And that's how, in this particular problem, you'd come up with all the missing information for your formula. So now once we plug everything in, we have 1/2 times 8 for the apothem, 3 for the number of sides of a triangle, and 16 square root of 3 for the side length of that triangle. And again, leaving everything in simplest radical form, we would just multiply the 1/2, the 8, the 3, and the 16, and we would leave the square root of 3 on the end of it. Remember, our rules are outside numbers times outside numbers, inside numbers times inside numbers when dealing with radicals. So this would leave us with 192 square root of 3 square centimeters. So now that I've gone through 3 different examples with you, I'd like you to do the last 2 on your own and see how you fare. So number 9, the side of a regular hexagon is 16 feet. Your job is to find the area of that hexagon in simplest radical form. This is another example of a problem where you have to find that central angle and then use half of that so that this is a special right triangle. The area you should come up with is 384 times the square root of 3 square feet. Now lastly, your job is to find the area of a regular pentagon with 7.2 foot sides and a 6.1 foot radius. The key to this problem is you have to notice that you have 2 sides of that small right triangle that would allow you to use Pythagorean theorem to find your apothem. If you found an angle for this one, you'll notice that it's not a special right triangle. You cannot assume it's a special right triangle. You have to actually find that it is by doing the math. So when you find this apothem using the Pythagorean theorem, leave the apothem, as the square root of 24.25 instead of rounding it. Plug that whole thing into your formula so that when you round to the nearest thousandth, you get 88.640 square feet.